What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of understanding how large language models, LLMs, specifically autoregressive models, AMs, utilize the tasks they have learned during training to solve new tasks. The algorithmic dataset introduced in the paper consists of modular arithmetic tasks where the model is required to learn linear modular functions and perform modular operations in context. The main objective is to investigate how AMs develop the ability to compose and generalize solutions by combining the tasks they have learned during pre-training. The study focuses on the emergence of in-context learning, ICL, and out-of-distribution generalization on modular arithmetic tasks, exploring the impact of factors such as model depth, task diversity, and task difficulty on the model's performance. The method aims to shed light on the mechanisms by which AMs transition from memorizing specific tasks to developing a more universal approach to solving tasks algorithmically, ultimately improving our understanding of how these models learn and generalize across different tasks.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method or algorithm works by utilizing a transformer model with a depth of at least 2 to develop in-context learning, ICL, and out-of-distribution, OD, generalization on modular arithmetic tasks. The model is pre-trained on a dataset containing a finite collection of discrete modular arithmetic tasks, where each task involves learning a linear function over z_p from examples provided in context. During pre-training, the model learns how to solve the pre-training tasks and later develops a generalizing solution by combining the solved tasks. The model's ability to generalize out of distribution is primarily determined by the number of pre-training tasks. As the number of tasks increases, the model transitions from a task memorizing solution to one that generalizes out of distribution. The model then adopts a more universal approach to solve tasks in context, determining the task vector algorithmically at inference time. The algorithm involves rescaling in-context inputs, performing linear transformations over GFP, and combining in-context examples to derive the answer. The model learns essential skills such as modular mapping, multiplication, and addition to perform modular arithmetic tasks effectively. The model's attention heads play a crucial role in implementing these skills, with specific attention patterns and structures indicating the model's ability to combine in-context examples and perform modular arithmetic. The model's performance on the OD test set improves as it gains the ability to generalize out of distribution, showcasing a transition from memorization to generalization as task diversity increases.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include the emergence of in-context learning, ICL, and out-of-distribution generalization on modular arithmetic tasks. The model's ability to generalize out of distribution is determined by the number of pre-training tasks, showcasing a transition from task memorization to generalization. The model develops a more universal approach to solving tasks in context, leading to improved few-shot sample efficiency and the ability to solve new tasks not seen during training. Additionally, the method provides insights into the competition between memorization and generalization circuits within the model, highlighting the importance of task diversity in achieving effective learning dynamics for out-of-distribution generalization. Practically, the method allows for the development of models that can generalize to unseen tasks and input vectors, showcasing the model's ability to combine in-context examples and perform modular arithmetic operations. The interpretability analysis of attention heads provides insights into the essential skills implemented by the model, such as modular mapping, multiplication, and addition, which are crucial for solving tasks algorithmically. By understanding how the model learns to combine equations and perform tasks, practitioners can gain a deeper understanding of the model's decision-making process and potentially improve model performance in various applications. Overall, The method offers a structured approach to studying skill composition and task generalization in large language models, providing valuable theoretical insights and practical implications for model interpretability and performance optimization.
How is the method validated or tested?
The method is validated or tested by examining the solution found by the autoregressive model, AM, after optimization on the modular arithmetic tasks. The analysis shows that the solution obtained by the AM is qualitatively different from linear regression cases studied before. The study focuses on the number of training tasks n_i, d, and the number of examples per task, alpha, to determine the model's ability to generalize out of distribution. The validation includes observing the model's performance on different sets such as s_i, d_train s_id_test s_o, od_train and s_ood_test. The model's generalization ability is assessed based on the accuracy on these sets, with a focus on the transition from memorization to generalization as the number of training tasks increases. Additionally, the study evaluates the model's performance on the OD test set as a function of training steps and task diversity, showcasing a memorization to generalization transition. The validation also involves comparing the model's behavior with different depths, d = 2, 4, 6, to observe how model size impacts performance. The method is further validated by analyzing the model's ability to combine in-context examples and perform essential skills like modular mapping, multiplication, and addition, which are crucial for solving the tasks algorithmically. The interpretability of the model is also assessed by examining the attention heads responsible for implementing these essential skills, providing empirical evidence to support the claims.
What results were achieved with this new method?
The new method achieved several results with the novel algorithmic dataset, designed to investigate skill composition in autoregressive models, AMs, on modular arithmetic tasks. The main findings include 1. The AMs developed a generalizing solution by combining pre-training tasks, showing a qualitative difference from linear regression cases. 2. The models exhibited a transition from memorization to generalization as the number of training tasks increased, leading to out-of-distribution generalization. 3. The model's ability to generalize out of distribution was primarily determined by the number of pre-training tasks. 4. There was a trade-off between memorization and generalization as the model gained out-of-distribution generalization ability. 5. The model learned to perform in-context learning, ICL, in both in-distribution and out-of-distribution scenarios. 6. The model's performance on the pre-training set and out-of-distribution test set degraded as model capacity decreased. 7. The model implemented an algorithm involving rescaling inputs and performing linear transformations to achieve out-of-distribution generalization. 8. The model learned essential skills such as modular mapping, multiplication, and addition to combine in-context examples for prediction. 9. Attention heads in the model were identified to implement these essential skills, with the model showing structured attention maps and PCA projections related to the tasks. 10. The model's ability to combine equations via skill 3 was superior in deeper models compared to shallower models, leading to better performance in out-of-distribution generalization.
What are the limitations or drawbacks of the method?
The limitations of the method outlined in the paper include the focus on algorithmic datasets, which may not directly translate to real-world language models. The difficulty in mechanistic interpretability analysis for deeper models poses a challenge in understanding the role of each component in the network. Additionally, the paper acknowledges that without further investigation, it is unclear which insights from the algorithmic datasets can be applied to more practical language models, and which are specific to the current experimental setup. This suggests a limitation in the generalizability of the findings to broader contexts beyond the specific tasks and models studied in the paper.